I'm happy to introduce you to uh, Sanmay Ganguly, who is going to take the first session today. And he did his PhD from TIFR, working on the CMS experiment, after which he spent his postdoctoral years in with with the CNRS Institute in France, and then Weizmann Institute, where he was working with one of the eminent statisticians amongst particle physicists. And then now he's a tenure track faculty in University of Tokyo, and probably soon he will come back to India to join the faculty of IIT Kanpur. So with that, over to Sanmay.
Okay, can you hear me all over the audience? Right, very nice. Let me check. Okay, this is changing. So I'm extremely happy to be here, and thanks to the organizers. Like few months back when I was asked to give some of the tutorials and 1 or 2 lectures, it's my great pleasure to get this opportunity, and I'm really happy. So like we will be interacting over a week, and the hopefully better. So and the topic I'm going to discuss mostly with you are sets and graphs, data structures, and how to do machine learning on them. Now, the prerequisite was like some hands-on basic introduction to machine learning, which all of you have. What I will use as for the programming language and the software is PyTorch. Now, in case you are not familiar, although there was an online tutorial, it's almost like NumPy, and we will all pick up together during the course of the talk, because you also have to code at some point of time. And then all the experts are here, then Elam is sitting at the back, and we all talk with each other, work with each other. So we can do all together. So don't get afraid of doing codes hands-on, but try them, and we will see how it goes. So as you can see from the schedule, I have total 5 days of interaction with you, where this day is almost totally, the first half is me, and then Vishal will help me in the afternoon sessions after lunch. And then we will have other ones. Okay, so I'm already red marked myself. I'm under trouble. My plan is that before each day, I will try to put the relevant codes in this GitHub. So for the first day, whatever code is required, yesterday I had put it. So from tomorrow, browse the GitHub once before coming to the lecture. And the plans are as following. So today, there will be an introduction to Deepset, introduction to graph data, and we will have one problem solving session where you will use the already provided code, and you will spend 1 hour or 2 hours coding yourself, and wherever you have a problem, we are there to help you out. But it's important on the very first day you get rid of the shakiness of these libraries. Okay. The second day will be introduction to graph neural networks and implementation in PyTorch geometric. Now, I had to walk you through some examples. So I picked up something called ParticleNet, which is very popular in CMS. So I thought, why don't we build it from scratch and do a whole training so that you know how to start it from a blank editor and build a whole professional working code. The fourth day will be symmetry equivariant neural network using message passing networks. And the final day will be some generative models on graphs. So this is my tentative idea. And let's see, it's okay if we don't finish all the topics, but it's very important for me at least. You people get the confidence to write codes of your own so that in the upcoming days, when you have a project in hand, you don't feel shaky implementing a message passing network for your project. So that's the most important part for me. It's not necessary you know all these things from these lectures and tutorials. Okay. Finally, just check this Slack channel. Everything, whatever discussions related to at least the GNN and sets that should happen here. I already pointed out to some public data set which we will use for the tutorials. And when you are asked to code something or when you download the codes, fork the repository. And if you want to discuss something, either put your fork public and put it here so that we can all look together and discuss, or you can make some pull requests. So after all the school is done, probably we can make this thing like a good public collection of codes which we build together, and we can refer it for the future. So, right. So let's start. This session will be no codes, but just overall view of what are the conceptual things we are going to discuss, okay? Any questions about the logistics? No? Very nice. First, let's start with some example of graphical data. They're everywhere, and in whichever context you can see information existing out there, whether it's on internet, whether it's in real life, we can find a graph representation of that information. So there are various kinds of graphs coming from different domains of science. So here you see in internet, when every day you open a newspaper and some advertisement pops up, it's using some graph neural network at the back. You play some music on the YouTube and you start getting suggestions. They are using graph neural network. Then you put like Facebook recommends you to add that person as a friend, bug that person. They're using graph neural networks. Okay. When we have drugs and proteins discovery and all this stuff, they're using graph neural network. And in last few years, there has been amazing research going on application of this graph and geometrical data set and merging the machine learning domain with differential geometry. So it's going on everywhere. And we will try to see how it's affecting our world of particle physics, where our data are resembling graph structures and how we are exploiting the power of graph neural network to improve our performance. So before going into high energy physics data, just let's look at simple, what is a graph? It's a mathematical object, an abstract object, where the information is like a set. What data is sitting on the set, it's completely up to you. There is no predefined notion. But the main important thing is that we have a set, and then we have an adjacency imposed on the set, that there will be always a pair, a subset of sets which will be connected through a pair. And if that subset is connected, we say there is an edge between those two pairs. So these sets elements are called nodes, and there are edges, and this is the basic graph structure. And we can put data on the nodes, edges. There can be global data associated with the graph. And maybe in some future lecture, we will discuss there can be higher order structures to graph, something like hypergraph, and there can be different properties associated to different nodes and edges. Those are called heterograph. But that's for the future lectures. For the time being, this is just simply a graph, and you can put any kind of data on it. Okay. By the way, just ask me any questions if you have during the talk. I will be happy to address. Yep. Sorry? Age? Let's say you have a bunch of elements in the set, and your data tells you there are physical reason to establish a correlation between a pair of two elements. Then you just define a relation between those two pairs by a data structure called age. Now, what that age does, it allows you to transfer information from one node to another. So if we just look into this graph structure, which is an example here, at first instance, let's say number 2 node can send information to 1, 3, and 4. But with one information exchange process, it can't directly affect node 5. Okay, so this is what the age does for you. It just allows you to exchange information. There can be meaningful information sitting on the edge as well. We will see all those examples. But just keep this abstract notion in mind that if your data set has a reason to establish a relation between a pair of nodes, you do that by establishing a data structure called age. Okay. U is a global data sitting on the graph. So a graph can has data on its nodes, which is property of each and individual node. It can have data sitting on the edges, and there can be one data which is not specific to a particular node or an edge, but it's associated to this whole mathematical structure. That's a global data. So that's why a graph can have data as a global data. There can be data on the edges, and then there can be data on the nodes. Okay, right. Now, in the previous transparency, when I said graphs are everywhere and gave you some examples from real life, it's important to understand how those data sets build a graph structure given the definition of the graph, which I just gave you. An image. The image is just a grid data structure where you have some pixel values sitting on different pixels. Some of them are 0. And you can initiate, like you take an arbitrary pixel here, and you can say, oh, I will treat all of these individual pixels as nodes, and all the nearest neighbors, I will establish a relation where I will connect these pairs. So those will be edges. And if you do that, immediately this graph has an adjacency matrix like this. Okay, so a graph representation of this grid will just become like nodes and this adjacency matrix. Then in the world of natural language processing, like each meaningful sequence of words which make a sentence, a meaningful language, you can just say that each and individual words and nodes and a meaningful grammatical relation builds a sequence and a relation. So that creates an adjacency matrix. And that's how you impose a graph structure on natural language data set. Proteins and molecular structures, they just naturally look like graph where you have all the bondings between the molecules and the atoms, and then you have some binding energies as age data, and some of them are like carbon. Oh, by the way, this is caffeine molecule, so we had some in the morning. Okay, and you impose some adjacency matrix to this. When Google gives you some traffic route kind of suggestion from going from one point to another, it just have nodes at each and every junction. It computes the path with real life data and give you an optimized path for the shortest time. Okay, so they are doing heavily graph neural network. So you can understand that when I claim that graphs are all around us, you can pick up any meaningful data set which is collected from real life, and you have a graph structure imposed on that. If real life, everywhere you see graph, high energy physics structure. This one? This one? Yeah. The adjacency matrices. It's only the connection. For the time being, it's binary inputs 1 and 0, that if there is a connection between a pair of nodes, it's highlighted as one of the colored ones. The number 1 is sitting there, and whatever is not filled up is 0. Okay. We didn't pose a global information on this graph, but however, here you can see that if there is such a complex molecule is at some excited state with an energy, then that value of the energy can be associated as a global data to this graph, right? Yeah. So it's not necessary to have always all the pieces of information associated to a graph, but those are the maximal set of information that can be associated, right? Okay. Now let's come to high energy physics. Like, I'm an experimentalist, so I will have some bias of showing you experimental data, but in theoretical high energy physics, where now the barrier is diluting each and every day in the context of applying machine learning in high energy physics, but we will try to see how sets and graph data structures naturally come out of high energy physics data. So what I'm showing you, something we called an event display. Okay, so this is nothing but like a proton-proton collision event recorded in Atlas, and bunch of energies are coming out bulk in the opposite direction. This kind of events are called dye-jet events. If you are not familiar with these terms, doesn't matter. It's not important for you. But what you should see that in real life, the data structure is pretty sparse. We do statistical analysis on many iterations of these events, right? We have large number of data sets, and each of them are completely sparse, where different regions of the detectors are collecting energy, and we have to represent the data and infer meaningful physics out of this. Here is a simulation for the HL-LHC tracks, and here is a bunch of dots sitting here and there. So we really need to have an efficient way to incorporate this data, and as I will discuss, most of the times when you have done a CNN kind of tagging or regression, where those methods turned out to be less efficient to represent data in high energy physics context because of the sparsity of the data. Because each time you repeat this experiment, probably a different region of this detector will be ignited. Each regions have different shapes and sizes. So a more efficient way of representing this data set is a graph, and why we will see. So the takeaway message from this slide is that given such distributions of sparse data in context of high energy physics, you can really take all the energy depositing voxels as nodes, and probably you can connect nearby nodes through some edges. We will see how to do that, and you can associate a graph structure with this kind of data. So like probably last year, there was a front page of CERN Courier which tried to highlight this, that if there are meaningful information from each part of a detector, then you can connect them through edges. How to embed that edge is something you have to define, but you can associate a graph structure. Okay. Right. So let's go through some key properties of the HEP data. This picture has been taken from this review, and I'm happy to say I produced these data sets for this. First of all, when you see something like, are you all familiar with particle physics data sets? Is there anyone who is not familiar with particle physics data set? You, what's your background? Phenomenology. Okay, so when you do so you should be familiar with like kind of simulations you do with PP and stuff like that. So when you do that simulation, you have a bunch of hard scattered patterns. The end state of them are like hadrons, photons, leptons. And when they come out, they release some signatures in our detector. So we register the spikes in different part of the detector. So when a charged particle comes out, the innermost part is something called tracker in a generic HIP experiment, where this magnetic field and the particles bend. And we typically have some tracker parts where there are dots, where they leave their signature, some silicon detector. Okay. Now, the problem of track reconstruction is efficiently connecting the dots when really the many dots are close by. So what you really do, you try to establish a graph data out of this and try to identify which edges should connect a pair of hits. Okay, so in that case, an optimal track finding problem becomes inferring the right kind of relation on edge. So it's an edge task in the context of a graph neural network. Our calorimetries are often layered, and when you have layered calorimeters, they have different granularities. So you just can't apply regular grid-based CNN methods out of the box. I mean, people have done that, but that's not the right ideal representation. So different layers, taking them as nodes, the energy depositing voxels, and you can connect the nearby cells through an edge relation, and this constructs a graph. In phenomenology, you can have like an event represented by different kind of object, like jet, leptons, and other stuffs. And then you can construct a fully connected graph combining the information of the 4 vectors and setting up a relation. So your event can be represented as a graph. So you can see that for a sparse data structure, which we often use in the context of high energy physics, there is a natural graph representation of them. And taking out meaningful information of these data pieces, if we use graph neural network, that will surely benefit us. Okay, so that's why our community is quite excited about graph neural networks. Right. So let's start from an example which all of you have done probably. You have done a CNN and for learning when you were learning machine learning. And in 2015-16, a concept called jet images became very popular in our community. So in case you haven't done a jet tagging, let me give you a brief overview of what's the statistical learning task we try to do. We have a jet, and which is a set of 4 vectors. So when we deal them in our practice, what we do, we take the constituents, their 4 momentum, which build a jet coming out of fast jet library. And then we try to construct a neural network, make a label out of our truth information, and then we try to perform a statistical learning task that we show this neural network several pairs of this data that given a jet what will be the truth label, and we do a supervised learning task, and we try to infer what possible patterns or particle this jet had originated from. Okay, so this is something I hope you have done. So there we implemented we try to do that if there are energy deposits from layered calorimeter, for just ideal cases, there people assume that all the calorimeter layers have uniform grid spacing, so they make like an RGB image. And we knew how to classify images. You have the convolution layers where there were kernels which contain the weights, and you did training to infer whether a jet image belongs to a quark jet or a gluon jet. Okay, so I hope you're familiar with this example. Now, what people try to learn from those images, mostly were on an average image the pronginase, which means if a top decays in a 3-body, you will have an average image like this, whereas like a gluon background will have a centralized average image. And the CNN filters were trying to distinguish the boundaries of such energy bulks. Okay. Now, this was in 2015-ish. And then in 2017, Kyle and his friends came up with ideas that if you have a shower, which the anti-KT algorithm tries to reverse engineer, it starts from all the particle, try to see what is the distance between a bunch of particles in the weighted distance in the eta phi plane, and tries to reconstruct. So they tried to reconstruct the same tree using learning on the adjacency matrices. So this was the first time the jet was represented as a graph in 2017, and they showed in a new reps paper that instead of average images, what will be the difference between a single QCD jet versus a hadronically decaying W jet. By the way, are the terms like hadronically decaying W jets and QCD jets are familiar with you? Anyone who has never dealt with jets? Fantastic. The next, probably 2 years down the line, or very next year, this was proposed by the MIT team Hesse-Thaler et al. They proposed a network for the same kind of tagging architecture, something called particle flow network. So they first defined that you have a network which first reads all the constituents of a jet, and then you do a sum pooling, and they named it energy or particle flow network. But what it was pretty evident that what they were doing is something called Deepset, and we will learn it today. And probably there was a variation of this network in the paper, which you will solve today as part of the homework problem. Hands-on, we will do it together. Once this was done, and they showed that they have very good discrimination power of quark versus gluon, it was becoming more and more evident that ideal representation of the jet constituent should be a set and not an image by itself. Okay. So until now, I was giving you examples of initially image-based representation, set-based representation. So now it's the time we should learn some underlying theoretical ideas of what we mean by machine learning on sets, and so on and so forth. So until now, whatever I said, are there any questions? Yeah. This. So this is something called particle flow network, and EFN were energy flow network, and EFP were energy flow polynomials, and probably you will code up one of these two in after lunch session. Okay, so we will see how to do that. Yes, Toshik. No, you have to decide which data is suitable to go on node, which. But once we choose a graph, so all the data in the nodes, all the data should be similar, right? I mean, for a homogeneous graph, for a heterogeneous graph, it can be different. So they can be different in size in different nodes. Absolutely. And the kind of data sitting on each node can be different. That's called heterograph. Sorry? Oh, normally this efficiencies of the jets and etc. are derived in phase space bins, because it turns out to be different. And if you make it out of all inclusive bins, then the power of these neural networks go down. So when we derive some efficiency or everything inside like a program like this, we always slice up the phase space and prescribe efficiency scale factors for a region of phase space.
I'm simulating some data. If I constrict my data to give me only events that are within this, I mean, that will require a huge computation power to generate a good amount of data to.
No, I think the idea would be, if you're trying to do machine learning, then in general, you have the weight you get from nature as dependent on the phase space region, right? For example, if you see just a PT distribution coming out of QCD, you see a falling distribution because the higher PT have lesser cross section. If you're building a training data for neural network training, you probably want a good mixture of events from all regions of phase space. And then you should build up your training data with taking samples from all the regions, and then just grab the efficiencies and RAW curves for all possible interesting phase space regions, which in general will be different.
I randomly give my neural network some event. I don't know which PT range it is.
No,
it won't be able to identify.
No, of course. So that PT will go as one of the features of the data. So it will identify.
But for example, if I give a signal event only, and it has to give me an output of, let's say, if I'm doing binary classification, it has to give me an output of 1. Right? If I'm giving a signal event that is of less PT than what I have trained it for,
no,
then it will give me it as a background.
For your particular example case, just PT as a feature is not sufficient, and you have to train the neural network with other features also, which will help it to learn and distinguish between signal and background. So PT is not sufficient enough.
Okay, so different layers I have to give. One can be a PT, one can be
no. All of the data should be stacked together and fed into a deep neural network, which has several hidden layers. And it's the task of the neural network to identify difference in pattern in the data set and try to label which data is coming from signal and which is from background.
I'm saying when let's say I'm preparing my data,
right?
I'm preparing my image, right? And instead of a grayscale image that contains only the PT deposition in, let's say, eta 5 pin, that contains only the PT deposition in the eta 5 pin, I have to give different layers of information to it, so that my network can identify it better, so that it is not only dependent on PT.
If PT is the only information you have, then the grid data with PT values as the entry, as a pixel entry, that's the largest information you can feed. But if you have more features which will help you to categorize an event better or a particular instance of data better, then you have to find out if, let's say, not only PT, but some, I don't know, some energy flow polynomial, any kind of other features that as a different channel in your image. Fine. I mean, that's, you have to decide how you're going to prepare your data and feed the information.
So adding those additional channels, will it help me recognize the image better if independent of this PT range?
If the data is truly meaningful, then yes, the more data is always helpful for a neural network to perform its task.
Give an image that is not within this PT range, and it is of signal, let's say binary classification signal, then it will also identify the
it will help, it will increase the statistical power of the neural network. I mean, it will still misperform in some cases, but on a bulk statistical data set, it will perform better.
Just very naive question. Within this, let's say, very short window of PT, I'm simulating, I'm generating some events. So what is a good statistics to work with? I mean,
And
how much
that depends.
simulated events should I?
This is not part of a general question and depends on your particular problem of interest. You have to figure out what's the cross section of the process you're interested in, what's the cross section of the background, and if the relative statistics given a phase space bin are compatible with each other. And that's how you determine how many events you should put in your training data and what's the composition of different mixtures of signals and backgrounds. So that's an user, from the user end, you have to apply your physics knowledge to determine that. Okay, good. Okay, I can move on. So let's see, what do we mean by machine learning on sets? Let there be a set with some n elements, and each element has a data which can be a k-dimensional, like it's in general defined as Rk. Okay. And this forms a set with cardinality n. This is just the definition. What do we want? What are the basic properties of a neural network which has to be there for a set? So let's say we are demonstrating with an example of a set with 5 elements. So x1 to x5 are the 5 elements of a set. You have a neural network which gives you an output y. First requirement that a neural network acting on a set should have is permutation invariance, which means that there is no predefined order of the elements of the sets, and you can shuffle the order of the set elements at any way, and the output of the neural network shouldn't change. This is called permutation invariance in the context. Now, once permutation invariance is achieved, how do we approach? So the example I gave you is mathematically written as this, that if there's an input set X, if you perform a permutation, you should get back the same thing. And just for the example, if you have 4 numbers, and let's say the canonical order 1, 2, 3, 4 has been permuted to 2, 4, 1, 3, this should be the representation of the permutation matrix for this case. Okay, and a set of all matrices coming from permutation of n objects forms a group. Now, how do you construct a neural network F which satisfies this criteria? So if you have these 5 elements, first you take a function psi, which is a neural network block, and make it act on each of these elements individually. And let's say H represent the latent representation which is coming out of this neural network psi. And once you have these H pieces, then you do a permutation invariant operation on them. You can collect all of them and take a summation. You can collect all of them, take the maximum, like this, a permutation invariant operation. And on that, you can already apply another set of neural network phi. And the neural network you make in this way is called Deepset. So the invariant Deepset layer is this one. This doesn't depend on the particular order of the element of the x. And if this is the representation of the function f, then by construction, it will satisfy this property. So this is called Deepset. And we will see in the tutorials, there is something called permutation equivariant operation, which is written in this way. Why this is permutation equivariant, this we will discuss when we do some hands-on coding, and we will see that explicitly. But remember, this is what is called a deep set, which we will code. Now, in the same context, when, by the way, how long this first session is going to happen? 10:30, okay. 20 minutes, okay, very nice. This is what we learned on the sets. Now, what do we have the corresponding criteria on a graph? Now, as you already know that from when you go from a set to graph, you have to induce an extra data structure called adjacency matrix. Now, if you perform a permutation on a graph, you just can't permute the nodes but you have to permute the adjacency matrix as well. And in this basis, if the permutation matrix is P, then PAP transpose is what the updated adjacency matrix looks like. It's just the same set of connection, you have relabeled the nodes. So this picture mathematically means this equation, that you had initially a data structure X and an adjacency matrix A, which formed the graph. You have performed a permutation, and the feature vector X went to PX, the adjacency matrix went to PAP transpose, and these two numbers should be similar, the same, and that's what is called the invariance, permutation invariance. And then there is another notion of permutation equivariance, which says that if you perform a permutation, the updated representation should be permuted in the same way. And this is called permutation equivariance. So we will see during the tutorials an example of probably tomorrow. What is meant by invariance and equivariance of permutation on a graph, and you will also solve one problem for that.
The second P before F mean, because P is permutation on the X, but F is a different thing, right? Different.
Right,
object.
but it was a permutation on a set.
On a set.
So let's say a set of 5 elements, x1 to x5. If you, and after it goes through F, it becomes a set of h1 to h5. Okay,
So
but when you perform the permutation on a set, the order of the elements should change in the same way. That's what it means, that an updated set of elements, think is at H or something, but the same permutation operation should
But
act.
let's say the output is a simple scalar, then you don't have this.
Then you will have an invariance. A scalar doesn't change under.
So that is already anyway invariant.
Yeah, by construction. Right? Yeah, so that's what it means as the permutation. The label on individual nodes changed.
No, the length of the connections. So that
Oh,
has to be preserved.
right now the length of the connection doesn't have a meaning. It's just it has a connection, and that's the information. Yeah.
That's why the adjacency matrix has just one in binary, right? No,
Yeah. So if there is an edge, you just associate a number 1 to identify there is an edge. That's a binary decision. The length doesn't have a meaning in this context.
What you're showing here, both the sets are actually labeled by 1, 2, 3, 4, 5.
Right.
So it's just the embedding is still the same. If you had like 1, 2, 3, 4, 5 and A, B, C, D, E or something, then it would have made sense what we mean by this permutation.
I mean, what I hear, all I mean is that when there is an F acting on the nodes, each of the elements have new data sets sitting on the nodes, but it's just the relative like labeling on each of the nodes have swapped, and nothing changes because you have relabeled the nodes. No data set, meaningful information is updated due to that. No. For a directed graph, it's not a symmetric matrix. And we will see an example of that. Sorry? The cardinality of the set should be same. So X can be a data of, say, 3 dimension. Okay. And f of X can be a data of 5 dimension. Yes. So let's take this example. Where is a good place to write this way? Or? Okay. So let's say you have one number, one set, which is like 2, 4, 6, 8. This was a set. It underwent through some f. So this, you will say you have a set of 4 elements where each element has dimension 1. Now, let's say you act a particular neural network, which was matrix W, which is of shape 1, 3. Then the output will be some number, I don't know what, depends on W, but that should be a number of 3 dimension. Right? Are you following me? So this tells you that the individual dimension of the data sitting on each pieces of node is different. So in this context, the data X and Fx can be of different dimensionality. What I'm talking about, the permutation here, is the relative order of these elements. And the way you swap these elements after permutation, P of f of x means this vector will be swapped in the same way. Okay, so this is what it means. But in general, the dimension of the features sitting on x and fx can be completely different.
So I have a question. So you're just shuffling the order. So adjacency matrix remains the same, right?
No, it also undergoes a PAP transpose.
So in the second graph, you see the connections remain same, right?
So this one actually represents this equation. So the connection is A in this context. After you relabel the nodes, it has become PAP transpose.
But the edge labels you see, those connections will remain the same, right?
Okay, so probably there should be a 1' and 2'. Like I copied this images from this website. So there should be new label on the edges. Okay, and in these new labels, in the 1', 2', 3' basis, if you write the matrix A, so A prime should be PAP transpose. That's what it means. Yeah. Yes. There, we will work out an example. There can be data sitting on the edges, and there should be, then you have a matrix with meaningful data sitting on the edges, and to construct this kind of construction, that data matrix also needs to be given a similarity transformation like this. Right? Okay, good. More questions? Okay. Right. So now let's go through a little bit of graph neural network. How do we construct? So right now, you are familiar with that in a graph, if there is a node, there is a subset of nodes which are connected via edge, and that's called the neighborhood. So this is the definition of neighborhood, and all the data sitting on the neighborhood for a target node I is defined as x on ni. So the first step of a graph neural network is just to identify the neighborhood, then act a particular neural network G, which will combine data from the neighborhood and the data sitting on the node itself. And the updated representation, which we were talking about, should become like this. Okay, so you have a neural network which has combined the data from the neighborhood, and then you update the data sitting on each node through another piece of neural network. So this is defined, like represented in this image. So let's say this is your target node. It can collect information from all the neighborhood to which it is connected via an edge. And then the updated node representation will be a combination of all the collected information and the data sitting on the node itself. So this is the 0th step of concept of what we called a message passing network. So a target node has received messages from all the neighborhood through the connected edges and updated the latent information sitting on the node itself. Well, pooling has a different meaning. Pooling means, in this context, that you gather information from all the nodes, and there is a permutation invariant operation which like washes off what was the order of the nodes in the neighborhood and things like that. That's an operation called pooling here. You can call this operation gathering. That's more meaningful in this context. That does depend on the direction of these edges. It can be that there is an edge direction from here to here, but if you have a graph where the direction of the edge is from this direction to here, then this particular node can't send information here. So for a directed graph, of course, the direction of the edges are important for a message passing operation. If your data structure tells you that the adjacency matrix should be built out of KNN algorithm, then of course you can, yes. But that's, as an user, you have to decide, right? Right. So let's walk through what are the general methods of graph neural network. First, the graph is a data which is the feature vectors and the adjacency matrix. Once you do a message passing operation, all the latent representation of the nodes are updated. Okay, and then once it's done, you can have different class of GNN operation. You may want to learn some data on the nodes. Then on each node feature, you apply a node network, and you can do node classification, node regression, etc. And we will see what's an example of this. Then there can be another method of graph classification. You can just, after few iterations of a message passing network, you can gather all the information sitting on all the nodes and combine them in a permutation invariant way. So this is, in your language, what is should be pooling. This sum O plus operation, which gets rid of the ordering of the nodes. And then you can apply a neural network to infer some information about the whole graph itself. That can be something like graph classification, like that. And finally, you can pick up each individual edges from the learned representation, and you can apply some neural network on the edges to do some edge classification or edge regression, whatever task. So these are the kind of tasks you end up doing when you're doing a GNN, that you stack few message passing layers, and then you do a node classification. You can learn properties on the nodes, edges, or on the graphs. Okay, so in general, broadly, there are three categories of message passing network. So from the so psi of xj will be this updated representation h in the last slide. When the gathering information Cij, like the weight of the gathering, doesn't depend on the feature sitting on the node, it is called a convolutional operation on the graph. So this is the general definition of graph convolution network, where this gathering weight doesn't depend on the x. A general message passing network should collect information from all the nodes, create an edge data, and do the gathering. And we will later learn that when you just gather the information by a weight factor, which is computed out of all the features sitting on both the nodes, this is called graph attention network. So in general, and you can see that this is the most general definition of gathering and pooling, and all of these other methods can be thought of as a subset of a general message passing network. Okay. And we will explicitly code these things up to realize how to implement them. And then in 2018, Google DeepMind came up with the definition of a general graph network, where the definition of graph is like you have a global data, node data, and edge data. And this is the graph. So U is, in this context, a global data. This is the node data and edge data. So first, there should be an edge network, which should update the representation on the edges, followed by a pooling operation. Then there should be a node network, which should gather the information from updated edges and sitting on the nodes and the global network. That should be called a node network. This should update the information on the nodes. And finally, there should be a global update network phi u, which should take the updated edges, updated nodes, and the global representation to update the global data sitting on the edge. So when you have a neural network, which is stack of these three individual subnetworks, and the order matters here, first edge network, then node network, and then global update network. This is the most general graph neural network. This is called GraphNet. This is from this paper of Peter Battacharya et al. So just to understand in this context, what are the three different, like a full GN block is what something I described. A message passing neural network just combines the edge data and node data. And the deepset layer, which we already have studied, combines the node data and the global data. There is no, when you're doing a deepset, there is no concept of a neighborhood or adjacency matrix. It's just a machine learning on sets. Okay. And here you can see like some example that if you have a graph where the data is sitting on this particular node, then after few message passing iteration, how the message, the data gets distributed on different nodes, whereas depending on the adjacency matrix structure, if the initial data was sitting on this node, it's the same graph structure, it's just the initial data is sitting on a different piece of node. You can see different, at each different iteration of message passing, the propagation of information through different nodes is different. So this is just a visual representation of how the data gets distributed, diffused through all the parts of the graph through a message passing operation. And you're welcome to read all these good reviews. My very good friend Jonathan Shlomi wrote a wonderful one, who now is in industries. And then on the tracking, there is one. We wrote one for the snow mass. And this is a nice picture coming out of this particular review, which gives you a visualization that what is called a one-hop neighbor, two-hop neighbor, etc. That after you know that given a target node, after each iteration of message passing, where it can send information and from where it can gather information. And we will visualize these things through hands-on coding in the coming sessions. Okay. Right, so I will just quickly run through some examples of the theoretical, maybe, I don't know, it will be fun. Yeah. Yeah. So I want you to really code up sitting here one of the existing papers which you haven't read. Take the core message passing network and try to see, after learning and going through all the tutorials, whether you can implement it. That will be a fun exercise to do. Okay, so just to take away from this initial set of discussion, GNNs are turning out to be state-of-the-art ML techniques for app applications. And GNN has its own limitations, like can be like, if you do many iterations of message passing, there can be a phenomena called oversmoothing, which loses the power of this neural network. But it's a fun thing to learn, and I will hope that during this course of 5 days, we will gather new information and you will learn a few new stuff. So yeah, let's start. Thank you.
So there has been some questions, but please carry on. Ask some more. We have certainly some time.
You can ask here.
Or
if you
also,
have later, put it in Slack so that it can happen. Person A has the answer and person B is asking the question. So you should build a social network through graphs in the Slack and do message passing there. Okay.
Any urgent question that you want to ask? Yeah, if not, then we thank Sanmay for this session. I will come back after coffee.